Hello, I'm Aoyanyi. Today I'm going to talk about the integration by parts. Integration is a very important computation of calculus mathematics. Many rules and formulas are used to get integration of some functions. A special rule, which is integration by parts, is available for integrating the products of two functions. This topic will derive this rule, which is integration by parts formula. Also, some examples will help us to get our concept. For this video, I'm going to talk about the theorem, proof, and examples for this video. First, I will explain the theorem for this topic. More generally, in mathematical analysis, integration by parts or partial integration is a process that finds the integral of a product of functions in terms of the integral of the product of their derivative and antiderivative. It is frequently used to transform the antiderivative of a product of functions into an antiderivative for which a solution can be more easily found. The rule can be thought of as an integral version of the product rule of differentiation. And this is the integration by parts formulas. What is integration by parts method? This method is very useful in order to master that technique of integrations. Many times we have to integrate the product of two functions. Functions often arise as the product of other functions, and so we have to integrate these products. Now I'm going to show about the proof of this formula. We are going to derive the formula for integration by parts, which could really be viewed as the inverse product rule, integration by parts. So let's say that I start with some function that can express as the product ux and vx. Let's take the derivative of ux times vx. Let's apply the derivative operator right over here. And we just have a review of the product rule. It is going to be the derivative of the first function times the second function. So it's going to be u prime x times vx plus ux times the second function. So it's going to be ux times v prime x. This is all a review right over here. The derivative of the first function times the second function plus the first function times the second derivative function. Now let's take the antiderivative of both sides of this equation. If I take the antiderivative of what I have here in the left, I will get the antiderivative of ux times vx dx, and going to be equal to the antiderivative of u prime of x times v of x dx plus antiderivative of u of x times v prime of x dx. Now what I want to do is I'm going to solve for this part right over here. And to solve for that, I just have to subtract this business from both sides. And then if I subtract this from both sides, I will get the u of x times v of x minus subtract the antiderivative of u prime of x times v of x dx equal to antiderivative of u of x times v prime of x dx. So this is the formula for integration by parts. So this right over here tells us that if we have an integral or an antiderivative of the form u of x times the derivative of other function, we can apply this formula. This formula is known as the integration by parts. The formula is very useful for solving complex integration problems. In some questions, we will see that it is sometimes necessary to apply the formula for integration by parts more than once. This gives us the method of for integration, called integration by parts. This method allows us to integrate many products of functions of x. We take one factor of the product as u. This also appears on the right-hand side along with du dx. The other factors is taken to be dv dx. On the right-hand side, the only v appears. Now I will show you some examples for this topic. Here we are trying to integrate the product of x of two functions x and cosine x. To use the integration by parts method, we let one of the terms be dv dx and the other be u. See from the formula whichever term we let equal u, we need to differentiate it in order to find du dx. So in this case, if we assume u as v as x, so when we differentiate it, we will find dv dx equal to 1. For example, simply a constant. Notice that the formula will replace one integral, the one on the left by another, and the one on the right. Careful selection of v will produce an integral which is less complicated than the original. With this choice, by differentiating, we obtain dv dx will equal to 1. Also from du dx equal to cosine x, by integrating, we find u will equal to antiderivative of cosine x dx, and it will equal to sine x. Then we use the formula that we discussed just now, and we will get the antiderivative of x times cosine x dx equal to v times u, and subtract the antiderivative of u times dv dx, which is antiderivative of sine x times 1 dx, and this will equal to x sine x plus cosine x plus c, where c is constant of integration. Now we go to the second example. This example is antiderivative for x times e to x from log 2 to log 4 dx. At the first, we have to choose which to be u and which to be dv dx. For this example, I will choose the u to be x and dv dx to be vx, and then we can get the u prime x equal to 1 and the v equal to ex. Apply the formula, it will equal to x times e to x from log 2 to log 4, subtract the antiderivative for e to x times 1 from log 2 to log 4 dx. The second step is we copy this part and we solve this part, and then it will going to be e to x from log 2 to log 4 is because the antiderivative of e to x is still itself. For the third step, we have to apply the formula which is the ub times vb minus ua times va. So we can get the log 4 times e to log 4 minus log 2 times e to log 2, and then minus the e to log 4 minus e to log 2. So we can get the log 4 times 4 minus log 2 times 2, and we will get the 4, and this will get the 2, so it's 4 minus 2. So we can get the 4 log 4 minus 2 log 2 minus 2. If we want, we can play with the logs a little to make this formula prettier. We can see that this is 4 log 4, then we can change it to 4 log 4 to 4, and this we can change it to log 2 to 2, and you calculate, and you can get the log 64 minus 2. And finally, we come to the last example for this proof, which is the antiderivative for x to 7 times ln x from 1 to ex. As before, we have to choose the u and v prime. In this case, I will choose u to be ln x and the v prime to be the x to 7. So we can, for this example, I will choose u equal to ln x and v prime equal to x to 7. And finally, we can get u prime equal to 1 over x and v equal to 1 over x times x to x. And then we can apply the formula, which is ux times vx, which is v times u, which is 1 over x times x to x times ln x from ln 2 to ln 4 minus 1 over x antiderivative for x to 7 from 1 to e to 3 dx. For this part, we can get it from integration antiderivative from 1 to ex for v times u prime, which is 1 over x times x to x times 1 over x dx, and we will get this part. I'm sorry, I have a mistake. For this. This should be 1 and this should be e to 3. And then we can get this part to be this part is going to be 3 over 8 times e to 24 minus 1 over 64 times e to 24 minus 1. And finally, we can get this answer. So, for the conclusion, the parts common in the integration tools package makes a closed equation, but not a closed expression containing more than one integral. Also, it acts formally on an integral for which the supplies u is inappropriate, but it need only be given u, not u and v. In the didactic environment, rules will remain the best alternative, mainly because it requires the student to provide v as well as u, and behaves nicely in an equation and in the presence of more than one integral. Despite its shortcoming in an expression containing more than one integral, in a production mode, the parts common would be the tool of choice. Thank you. This is all my presentation today.